and thanks for the introduction, and thanks for the invitation. It's really inspiring to be able to give this talk in Boston University in ACMW chapter. So thanks again. Before we go with the journey of shapes, I will start with who am I? A little bit, just a little bit. So I did my undergrad in Middle East Technical University in Ankara, and I have a bachelor's in computer science and a minor in electrical engineering. And I had some internship in a research lab called Kovan, and that is a swarm robotics lab. So that's how my interest for robotics, vision, and graphics started. Then I came to Purdue, then I came to US for the first time. I was not with my parents, I was living alone, etc. So I came to Purdue to do my PhD. On the way, I also got my master's, and my topic was proceduralization, which you will also see during the presentation. So I'm not explaining what is just yet. Then during my PhD, I did a lovely internship at Pixar Animation Studios, and I have worked and collaborated with many companies, and I can say that Pixar is still the most magical place you can ever work. Then I finished my PhD, and I was focused on doing a postdoc in academia and be a professor, open my own research lab, like, you know, all that PhD dream. But then I was about to do a postdoc at MIT. Then my postdoc advisor at that time said that, oh, you know what, I'm going to Facebook. Do you want to come to Facebook and do a postdoc there? And I said, sure, MIT, Facebook. Yeah, why not? Then I joined Facebook as a postdoctoral research scientist, and I worked on deep learning and machine learning models for spatial computing, for map extraction, and then in Oculus for VR, human understanding in VR. And these are some of the projects that you can search for. The first two are for mostly for understanding satellite imagery, and the last one is a data set that we published for eye tracking research. Then I left Facebook because of some reasons that let's talk about that later. And I joined a startup. I took an adventure, joined that startup called DeepScale. And meanwhile, in the first half year when I was working in DeepScale, I was also visiting scholar in IPAM in UCLA, and 1 week I was in SF, 1 week I was in LA, so I was like flying in weekends, and it was some like very like work time, but it was very fruitful because all the 3D deep learning collaborations and all the like learning from data for geometry collaborations are actually have some roots and have very nice theoretical background discussions in IPAM. So I owe most of it to them. And in the startup, I looked mostly at temporal models and did research on how we can solve autonomous driving for using like temporal models, or like converting spatial models to temporal models, spatial models, etc. And if anyone is wondering what happened to the startup, it is bought by Tesla. After it is bought by Tesla, I didn't want to work for Tesla. And I don't know what you think about Tesla. I don't want to go into that discussion, but like I didn't want to work there. So I searched for jobs, and I was saying, oh, should I go back to academia? Should I do another postdoc? What should I do? Then I found the most impactful research I could ever do. So now I'm in Intel, and there is a small group in Intel, about like less than 30 people, called Intel Studios. And we are actually in the world's most unique stage. It is the biggest capture stage in the world that is doing productions like AR and VR productions to do volumetric video. And that is like the future of filmmaking, because from 2D, there's no longer 2D filmmaking. We will go volumetric and 3D filmmaking. And the stage can capture up to 30 people simultaneously acting at the same time in 10,000 square dome. So it is lovely. If anyone stops by in LA, I can give you a tour of the dome. So that is me. If any questions about my path or this unusual jumping from startup to corporates, etc., you can ask at the end. So let's start with the topic. So I will just start with this video saying that there are many buildings here. You can see that this is New York, but this is actually a new New York. This is a generated model with traditional like procedural models, but the actual grammar from the for the procedural model is extracted from, is automatically extracted from a model. So my question here, you don't need to know anything that I just said, but how many buildings do you think are there to the making of this, for the making of this model?
Like in this model?
Huh?
Like in this model right now?
Yes, yes. So in Manhattan, normally there are 4,000 buildings. So you can say anywhere from, I don't know, like 20 to 4,000. How many actual like information, if you compare the information, how many building information is here?
3,000.
It's actually just 200. So today we will see how to obtain such representations to generate complex real-world scenes like this with compressed and generative models in 3D and traditional settings. So this is just less than 200 buildings making up this new New York. So in a nutshell, the process to obtain such representations is called proceduralization. And we start with a geometric model like this and proceduralize it to extract its grammar. Then the grammar can be edited just like text-based editing or visual editing to generate different geometry. As you see, there are like windows are different. Or even more different geometry, just like adding one offset and one repeat operation, you can like create this village. And randomizing the heights, you can just create a city from this model, just editing some lines. So let's first have a look at the need for such content. So the technological developments in the last century have carried us from a few pixels per screen to infinite worlds like this. And this pushes the bottleneck from the technology to the content. In particular, architectural models like this have always played an important role in areas like computer graphics and virtual environments and urban planning. And due to the size, detail, and complexity of such models, the proliferation of such areas and the demand for such urban models has significantly increased. So how can this demand be satisfied, or how can the content problem be solved? So manual modeling is a solution, but you know, even the fastest of the humans is a little bit slow when we want to automatically create content. We can use procedural modeling, but procedural models are hard to write and control, and you need to write like detailed grammars. And you can recycle existing data, but they usually lack structural information, and that hampers efficient reuse and synthesis of such models. So the question is there a way to combine such approaches for both efficient content generation and modeling? For those of you that is coming from machine learning or like more like new computer vision backgrounds, maybe they may not know procedural modeling. So let me just give a very brief information. So procedural modeling is generating buildings, plants, clouds, cities, worlds, whatever you can create with graphics using an underlying system of rules. And what I mean by underlying system of rules is a context-free grammar like this. So, you know, in context-free grammars, there is the starting symbol, the terminals, non-terminals, and the derivation rules. And here is the parse tree of such a grammar. So here, the starting symbol is the building, and all of those edges you see in the parse tree represent the derivation rules. And these, the ones that are
going.
Tammy, are you saying something?
What doing?
Just a second. Everyone, can you please mute yourself? I think I did that, but maybe someone unmuted. Sorry about that, Ilke. Can everyone please mute themselves? Sorry. Thank you. You can go ahead. Sorry about that.
Sorry. So just a very brief note, assuming that we are all like a small family here. Yesterday I had a talk and I had a Zoom bombing. So any noise that is coming through the mics, I'm like, who is that? What was the noise? Is there video? I'm like, yeah, you know, so I'm sorry about that. So I'm a little bit still very like, it was a very bad experience.
You felt jumpy, right? I read your
Yeah,
story on Twitter. Yeah.
yeah, it was so bad. I can't explain. And it's in like Instagraph and in corporate setting in Intel, and I'm like, and the worst case is my parents were watching because I was so proud of the talk. Anyway, sorry, too much information. Going back to the talk. So this is the parse tree, and these arrows are actually the derivation rules. And what we create by this particular derivation is this little building. So this little building is actually done by this grammar, which has this parse tree. So you can assume that all of the cities, etc., that I showed in the beginning are actually the product of a grammar like this. So procedural modeling is powerful. How can we use procedural modeling on already existing models to overcome the lack of control or detailed grammar writing and dependence on domain expertise? Because here the grammar is written by hand or by an expert that can write or code all the details. Can we actually, so what if we can obtain a grammar from a geometric input and use that for all the advantages of procedural modeling? Well, inverse procedural modeling actually does that, but it discovers the parameters and rules of the underlying procedural representation, not the grammar itself. So proceduralization, on the other hand, extracts the grammar directly from any given observation. So this is an overview of the proceduralization approach that is used to proceduralize 2D or 3D data by exploiting the hidden similarities and structural properties. And this framework provides the main phases of proceduralization that allows almost any geometric data to be converted into a procedural form. What I mean by any geometric data. So the input to our inverse pipeline may be images, meshes, or point clouds, or almost all content that can be categorized. And the granularity of the content also changes from buildings to cities to facades. And actually each image that I show during this pipeline slides are the exact input or intermediate output that I used during the processing, and they are not just exemplars. So this is actually one of the inputs of the mesh-based proceduralization, for example. So the first step of the pipeline involves segmenting the input into structures that are separable from their surroundings by significant changes. And that segmentation can also range from being purely geometrical to segments that only represents the semantics of the content. So for road extraction, for example, from satellite images, it may be just the road vectors, but for mesh segmentation, for example, it can be those domes or these regular repetitions on the windows of this beautiful architecture, etc. The second step of the pipeline labels the structures from the previously defined segments. And as in the previous step, it can be fully automatic based on the properties of the segments, or it can be manual labeling with semantic labels. And it can also range from all those different, like from facades to cities to meshes, etc. And the third step of the pipeline organizes segments and their labels into a hierarchy. And this hierarchy is needed to encode the spatial relations of the structures and to discover the underlying rules. So here we know what are the components. We know which components are similar to each other. Now we need to know that spatially where they are, or what are their relationships during the around the model, and how can we actually represent those in patterns or with pattern parameters or with regular rules or grid structures, etc. And after we know those, as you can see here, like we know repetitions, we know the rule is like that, or for city repetitions, we find the transformation matrices of each building relative to the parent of that neighborhood, or for meshes, we know where each mesh is located in the parent mesh, etc. So when we know all of those rules, we can actually extract it as a grammar, and that grammar can be a split grammar or an L system or a context-free grammar, etc. So most of them are mostly like shape grammars, as shown in the examples. So I will go through some of the examples. I will not like closely follow this sorry outline, but it gives an idea. So for point clouds, the first part, the shape processing part, is actually simple. It is a semi-automatic one. So for the next ones, they are all automatic, but this one is semi-automatic in the sense that if you want to proceduralize this point cloud, the user goes and selects a granularity, which is, for example, just a mouse stroke around this roof. Then within that roof, within that selected volume, we run the Ransack plane fitting and Euclidean clustering, and we then label them based on their similarity. And at the end, you can see that the point cloud is segmented. Of course, there are many segmentation algorithms that you can use, but since the motivation of this at the end is to enable the user to edit the model without exposing the procedural rules, we actually want to let the user decide the granularity. So it may be the case that the user wants to stop here and do not segment the individual windows, so that freedom is left to the creative people. For urban spaces, and the representation for the urban space is the huge textured meshes of New York, San Francisco, Chicago, etc. By the way, for all of those papers, I leave a pointer at the bottom of the page. So if you want details about that approach, you can just visit that paper. So for urban spaces, we have a nice, clever approach, let's say. So for each building, we actually have near and far cameras, right? Near and far planes for rendering with virtual cameras. So if you put both of the rendering planes at the bottom and incrementally change the near plane, going to camera looking top down, incrementally change the near plane, then you can actually see the building step by step. And when there is a significant change between those components, we say that, oh, okay, there's a new component. As you can see here, for example, we see that there is a significant change in the rendering. So we say that it's a new component. And why do we need those components? Because we want to represent these as the terminals of the grammar. And we also want to label these components, and for that, we actually extract features from each component as the albedo, window spacing, window fullness, etc. We have like a 15 element vector that we extract from each component. Then we do dissimilarity clustering to find those terminals. These are all instances of the same terminal. And this dissimilarity clustering is actually weighted. So you can, if you want to give, for example, more emphasis to the textures, you can have all of the similar texture buildings together in one cluster. Or if you want to give more emphasis to the height of the buildings, you can actually change the weight of the height feature and divide them into two different clusters. Anyway, so this is how we do the shape processing for the urban spaces for proceduralization. For architectural models, such as this one, this beautiful building here, our main motivation is to find all of those individual repetitions of domes and windows and components that are repeating in the building. I will not go into details for now, but we formulate this task as a set cover problem over the triangles of the mesh. So this is the input triangles, and what we want to find is as fine-grained repetitions as this one. So we formulate as a set cover, minimum weighted set cover problem that we want to find subsets that puts these together with two metrics, the neighborhood metric and similarity metric. So by merging and splitting clusters until convergence, according to that set cover formulation, gives us these repetitions and components all labeled by their similarity. We can apply similar approaches for satellite images, and this is when deep learning crawls into the equation. So for satellite imagery, we can actually apply road extraction. We can formulate a road extraction problem as a deep learning solution. Then we train several deep learning architectures to extract roads. These are all, so this is the ground truth, this is ResNet, this was VGG, and this is SegNet, and this is DeepLab. This gives us some prediction about the roads. Then we apply some thinning and morphological operations to strengthen the roads and apply orientation-based bucketing to extract individual road segments, concluding the segmentation step with vectorized roads. So these are all proceduralization applied in different domains, and we can even go to a completely different domain such as 3D printing and apply similar energy-based segmentation formulations for 3D printing. This is very similar to what I said for the mesh segmentation, but now our energy function is not optimizing for maximizing repetitions, but it's optimizing for near convex shapes, because when we are doing 3D printing, you want to have as much near convex objects to be printed to decrease the support material and to decrease the printing time. So we can also apply similar perspective to 3D printing. So on top of all of these shape processing approaches, we can actually apply grammar discovery after each segment. So now going all the way back to the point clouds, then after we segmented the point clouds, we can actually extract the patterns as a grammar to be used for editing, for creative editing. And in this paper, we actually presented a structure preserving direct procedural point cloud editor, which was the first point cloud editor that is directly working on point clouds, but not.
Thank you. Bye. Have a good day. Thank you. Bye. Yeah, I'll stay on. Yeah.
Bye, Vidya.
I think this person was a new person. Sorry about that. I think we just can mute the people who.
I do have a few things planned for our meeting.
I don't know how to mute her. Okay, got. Sorry, we just were able to. Sorry about that. We just were able to mute the people who were in. I think she just joined. Sorry.
No worries. So yeah, we can extract the grammar and use it for editing buildings like that. So this building in D is just a product of like 3 or 4 minute editing session from C, so which is a very nice contribution. We can also apply grammar discovery for urban spaces. So here we have a hierarchical simplification to organize based on similarity, and another hierarchical clustering is follows this to organize based on structure. And the main motivation here is that all of the city actually has some hierarchical rules where, for example, a landmark is always covered with office buildings, or the residentials always has a shop in it. And you can actually model the variance and model the standard deviation and mean of that structured rules throughout the city, so that when you want to create a new New York, you actually have the similar neighborhoods, not exactly the same New York, but similar neighborhoods, so that you can have that real city-like look. Instead of just putting random buildings together, you can actually preserve the rules of the city. For architectural models, this is a little bit more detailed because the models here, the buildings here are more detailed. So here we convert the components into nodes. Then we, it's like going in the inverse direction. So after we have the nodes, we create a split tree. Then we look in the split tree to find the rules that create the tree. For example, if there are those windows within that wall, what is the repetition? What is the spacing? Is it a regular pattern, etc.? So these are all automatically extracted from that hierarchy. Then we represent those patterns with the grammar rules. and you can actually obtain a context-free grammar from those patterns. Then those rules, those derivation rules and terminals and non-terminals are swept under the hood for interactive editing sessions. So in these editing sessions, you just like pull, push buildings or copy paste or split, and everything is procedurally generated in the underlying engine. But the user just sees that, oh, okay, I am pulling a wall, and instead of 2 windows, now I have 3 windows with similar spacing. Then one more window pops up, etc. Or when you copy paste, you don't need to like try to merge the geometry on the wall ending because it's procedural. It already generates and adapts. So going to the fourth one again, which is the road extraction that we did before. You can see here, we left it here, that this was a geometric processing part. Now we actually create our grammar on top of that. Why I say grammar in quotes is that here we actually don't have a grammar, but we have a generative street addressing approach. So just a very brief background about this. According to United Nations, 75% of the world is not mapped. Not mapped meaning there are roads, but those roads are either not vectorized on any map or they don't have any names. The addresses in those regions are like, go through the market, take the second right, or the third house on behind the mosque is my house, something like that. So all that landmark-based addresses are still being used in most of the, like 75% of the world. And this is a huge problem for economic growth, for voting, for political inclusion, etc. So this project in particular tries to address that using generative street addresses. And this scheme you see here is the core scheme for creating the addresses, which starts with the meter marker and the block name, which is followed by the region name and road ID, and actually this becomes the road name. So road is NK42. Then it is the city and maybe country information with versioning. And I don't have any slides on that, but the main motivation is to create those, is to just looking by satellite images, extract road vectors, group those road vectors into regions, and within each region, create a street address for every 5 by 5 meter in the world. This is deployed in some pilot areas that I can proudly say that there are some place in the world that uses our road addresses. So which is a nice feature of impactful research. Anyway, so following that, let's go a few of the applications. Here you can see that using the grammar, using proceduralization, you can actually do structure-aware synthesis on meshes and on point clouds. So in both of them, on the left is the original one, on the right is the synthesized one. And we can process different geometry, we can process different point clouds, etc. For completion and reconstruction, we actually have created an intermediate step for completion of the point clouds. So for example, here you can see the consensus model, and the consensus model is based on exploiting the discovered repetitions to create a collective better version per instance. Here, this is the original point clouds, and it is reconstructed using like traditional Poisson reconstruction. And here it is after the consensus model and the reconstructed version after the consensus model. And you can see that in the same model, just enhancing it with that consensus model increases both the point cloud quality and reconstruction quality. And 93% of the components are completed from 1.2x to 4x. For mapping, that is what I just talked about. We can actually, this is an interactive tool where you can query the addresses. It enables both forward and inverse querying, saying that like, where is 19AAA33 address, and it can find it, or you can click on the map and find that. And this is an example of the mobile app that that our partners were using. Actually, if Kanil is still here, yeah, he's here. So Kanil here is the creator of this app, and we are always, our team is always still in the loop for the open source version of the project. So I wanted to thank on behalf of everyone here to him, because he's all here listening. Thank you. And it's not only Kanil, but yeah. Yeah. You can say something. I see you unmuted yourself. You can say something.
Kanil, do you want to unmute yourself and maybe add a point on this? Maybe he's... Okay, I have to... okay.
Yeah, thank you, Ilke. I'm really happy, like, we are still in touch, and it brings us back a lot of memories seeing the demonstration again live, like sort of live. But yeah, that's all I have to say for now. Honestly.
Thanks for everything again. Anyway, so yeah, what I'm saying is our team is still intact and like still communicating, and like, yeah, thank you. So continuing with the presentation. Another application is, can we apply all of these proceduralization knowledge to actually learn the parametric representations and components in a deep learning setting. So all of the things that I mentioned before, except the road extraction part, was without deep learning, with traditional one. So from here, I actually want to jump into the main deep learning part. So we saw this, and in the deep learning setting, we can have this confusion about, is everything coming from the representation, or the generator is the important part and the data comes from the generator, or data both feeds the representation and generator. So in the deep learning setting, everything can be a little bit more, have more feedback loops between the representation and the data and the generator. And when we look at the 3D deep learning for shapes, this is like a very simple representation of any deep learning encoder-decoder network that you can see. And there is data in the input and the output. Then there is the representation in the input and the output, and the Latin representation that you can see in the feature space. And this part, the decoder part, can be formulated as a generator. And this is not the only representation, but just to give a very basic idea about what we say when we say deep learning for shapes. And of course, 3D deep learning for shapes can be for any task. You can classify, you can segment, you can match shapes, etc. But I will be mostly focusing on generative part, of course, following the first part of the presentation. We can say that these first subgroup of tasks are mostly passive. So it is, we are looking at the image, or we are looking at the shape, or we are looking at the model, and we are trying to find a specific thing from that. And the second part is actually active, which is also the synthesis part, which is we have some data and we are trying to create some other type of data, or morph the data, or reconstruct or transform the data to create something else. It's not just like looking and observing. And within that active deep learning tasks, we will look at generation. I know most of you know this, but just to set the vocabulary correct. Data is a collection of things with certain properties that the generator learns from. Data has amount, size, resolution, classes, completeness, distribution, and noise. And these are all properties of the data. Apologies. Now there is representation. The representation is initial, intermediate, or final format of the data. It's not the data itself, it's the format of the data that configures the data to live in some predefined space. The representation can be silhouette-based, or image-based, or volumetric, or point clouds, or meshes, or parametric or boundary representations, or skeleton representations, or it can be the latent space representation. And for the generator, generator is mostly the generative model that performs creating new things or converts the data into different variations of representations based on data. It can be within the same representation or different representations. And all the generative adversarial networks, variational autoencoders, blend shapes, procedural models, these are all generative models. The first two being in deep space and the second two being in traditional space. And my evil motivation behind all of that is, can we formulate and learn an implicit or explicit shape representation that mimics procedural models, which are explainable, interpretable, and controllable, following their parametric and hierarchical nature? Here, what I want to emphasize is the explainable, interpretable, and controllable part, which is for most of the generative models, especially for shapes, we have the latent space that we can find our way through, but there is no explicit, okay, I pulled this, I pushed this, and it behaves as I expect. So that is the actual controllable and interpretable part, and that is what is missing from the current generative models. Back to basics, what's a deep generative model? We saw the traditional generative models, not going to the deep generative models. Discriminative models, as I said, for analysis, and generative models, as I said, for synthesis. And this is looking at the observations and finding something from the observation. And this is looking at the distribution and finding new samples for within that distribution. If you want to be even more motivated about GANs, I think this is a question that was asked to Jan LeCun several years ago, and he said the most important thing, the most important breakthrough in deep learning was GANs, is adversarial training, and the variations that are now being proposed is the most interesting idea in the last 10 years in ML, in his opinion. And these are the cumulative GAN papers coming up every year, and Mona knows that in computer vision conferences, GANs are like exploding, etc. So I will skip these a little bit because you know the main idea behind generative models. We can have like, there are actually 3 types of deep generative models: the autoregressive models, in which the generation can be too costly or cannot be controlled. As you see, there are like elephants with 3 trunks, etc. There are variational autoencoders, and it maximizes the variational lower bound on log likelihood. But they are not asymptotically consistent unless the actual distribution that we want to achieve is perfect. And because of that, the samples are blurry. And these are like the vanilla versions. I know that there are many improvements over these, but this is like when it was the first it was first proposed. Then there is GANs, and as you all heard before, probably it's a game theoretic likelihood free model. It's a game between the generator and the discriminator. Generator is trying to trick the discriminator, saying that, oh, see, this is real, and discriminator is trying to find those tricks and say that, no, that is not real. So this is a very basic GAN where from a noise or from some distribution, generator creates some samples, and there is the actual training data with real samples, and the discriminator is trying to say this is fake, this is real, trying to find what is real, what is fake. I am skipping these details. There are famous GANs, like vanilla GANs is, as I showed before, there's conditional GAN that is putting conditional variables y into both the generator and the discriminator. There is bidirectional GAN that has that is both have the, like, if you see this part, this is the actual GAN, but there's also this backward part that is trying to find the actual latent version, of the starting starting distribution. And there are other versions like InfoGAN, auxiliary classifier GAN, etc. You can read those papers. Going back to generative 3D deep learning models, these are the representations for those. And the first part is the fundamental part, like images, volumetric, like images, let's say pixels, voxels, points, meshes, and graphs are most of the fundamental representations. And there's also the combined or enhanced versions like tablet-based or depth images or part-based, etc. These are depending on the fundamental representations, but they have some other information that is embedded. For image-based image-based deep learning models for shapes, actually for 3D, it all started with multi-view GANs. So we were very good with deep learning on images. So how to extend these? So instead of having one image per one object, people said that, okay, if I have a 3D model, I can have many images around that and have many CNNs for all the images, and combine them and do some classification. So this is one of the multi-view convolutional neural networks for 3D shape recognition, is one of the first 3D deep learning papers. Then came other image-based approaches. This is mostly for view synthesis by learning transformation. So you have a 3D object and you have a view from this angle. How can I actually create a view from this angle? And that problem is solved using deep learning in all of these other papers. But of course, image-based 3D deep learning have its limitations, such as it is limited by 2D convolutions. It fails to capture the global shape because you are always looking from some view. And even if you sample the whole sphere around that, you still have the scaling problem, and you have the view interpolation, etc. So the data is actually cheap because you can render from wherever you want, but there is always the view sampling problem. Then came the voxels. So if you can do something very good in pixels, can we actually add a new dimension to pixels and have the voxels? And for the convolutions, doesn't need to change as much. It's just like converting 2D convolutions to 3D convolutions. We have very good knowledge about all that, like spatial decompositions like voxels, octrees, KD trees, etc. So can we actually use those? And of course, like one of the very first papers are VoxNet, OpNet, OCNet, etc. And these are expanding what we know for 3D, for deep learning in 2D to 3D. So these are other volumetric models, and I know that there are like very nice advancements nowadays with occupancy networks. And if you haven't read that, it's not here, but like that's a nice paper that suddenly all of the papers are referring. So you can check occupancy networks for volumetric deep learning for shapes. And these are other networks that some of them are using the 3D conval STMs for shape understanding, or using in generative space, using DCGAN for generative space. Or there are part-based approaches that are learning to reconstruct parts based on 3D deep learning, etc. But for volumetric 3D deep learning, the resolution is always low because it's exponentially getting more expensive. For whatever we were nicely doing in 2D doesn't work as well in 3D, because for images, you have some information in every pixel, but for voxels, it's actually sparse representations that you don't have information for every voxel. Instead, most of the voxels are empty when you are representing a shape in 3D. For volumetric 3D deep learning, they can handle non-manifold models, but occlusions persist. And they almost need categories or templates for those different shape representations. Then came the point clouds. So we are going further away from pixels, that for voxels, everything was still in a grid. You had like, what I say, 3D pixels. Now you have those voxels in a almost random fashion that it is not structured. There is no structure anymore. Furthermore, for voxels, you can actually define some neighborhood, etc. But in point clouds, there is no connectivity. So the very first paper that came with that, probably all of you know, is PointNet. And PointNet, with that T-nets, transformer nets, PointNet showed that you can actually do deep learning on point clouds. So the T-nets actually replaced convolutions, and new loss functions emerged. They are not new, but like in the 3D deep learning setting, new loss functions were used, like Earth mover's distance or chamfer distance. And the most important thing is the critical set appears. And the critical set in that PointNet paper actually shows you that the outline of each shape is actually enough to represent that shape. So that is the critical set of points. And that is actually very useful when you are thinking about point clouds and what they represent, or how they represent, or how each point is important. So for point clouds, there came more papers, of course. So for example, there is the PUNet, point cloud upsampling network, for a different task that, like for sparse point clouds, can we actually preserve the shape while we are upsampling them? Or there's the generative ones like shape generation using spatially partitioned point clouds like this. Many others follow through. And I think the learning representations and generative models for 3D point clouds is one of my favorites, this second one, that they show that you can actually do point cloud arithmetic in latent space, where like you are just like adding and subtracting two latent vectors, and they actually have a meaning of, let's say, arm holders for the chairs or the table legs, etc. So that's a very nice paper. For point clouds, there was also limitations. It is constant data to begin with. What I mean by constant is not relative. It's an ordered set and needs permutations or relative embedding. And grids, graph, manifold, surface points, these are all to discover the point clouds, how to organize the point clouds. And there's also intermediate representations like PCAs within the point clouds, or 2D folds, or Gaussian mixture models, etc., to have an intermediate representation that you can base your parameterization on. And there's no invariance to deformations. Then came the meshes, and only mesh-based approaches are actually interesting in the sense that they are trying to construct those novel convolution operations based on meshes. And you can actually learn more about the AtlasNet or MeshNet, etc. And very parallel to both point clouds and meshes, there are also graphs and manifold-based approaches, which I personally see the most feature in. For example, the spatial and spectral models for graph-based deep learning models actually create very novel approaches for shape matching, for generative models, etc. And the most novel idea here was using LB the Laplace-Beltrame operator on meshes, so that you can have a the basis of functions that cover the model. Then how can you actually do shape matching, or how can you extract that shape signature, use that shape signature for novel operations? Other novelties for graphs and manifolds is using like geodesic polar coordinates, which removes the dependency on the ordered set of ordered setness of point clouds, etc. And the limitations for those are complex explicit functions. They may need a metric space. And for LB, the basis ordering is important, so there's isometric mismatch. So any function in your basis may not be in the same order with the same shape in a different pose. And it is mostly for feature learning, not for generative models, but nowadays there are coming more models, more architectures. Finally, there are grammar-like approaches which combines the proceduralization and the deep learning part. These are very novel approaches that are trying to mimic shape or write programs from given parts to assemble those parts by programming, or using some molecule-based approaches in procedural modeling, like this, as if the molecule strings are similar to procedural strings, etc. And the limitations, the hierarchy is not extracted, that is imposed. The rules, primitives, parameters are predefined, they are not extracted, only the parameter values are extracted. And the grammars are completely limited. So for example, in this one, you only have add and subtract, there is no other rule, etc. And of course, it's representation bound. So open questions: can we learn global shape descriptors in parametric space without templates, without classes, hierarchically, or in a guidable manner? And that is me. I can take any questions you have.
Hi, Ilke. Before getting to question, I just want to say that I'm just gonna stop recording.